Welcome to the Mobilize and Restore webinar series, and thanks to those who have continued on from the research talk. In this portion of the webinar, our speaker, Kate Clancy, will discuss best practices for and share lessons learned from working with OpenSim Moco. In particular, she will discuss strategies and provide examples she used to iterate and refine her Moco optimization problem and choose different settings. So again, we'll take more questions at the end of the best practice session, and again, use that Q&A panel. And feel free to enter any of the questions as she is talking. So with that, Kate, go ahead and start the best practice session.
Great. Thanks, Matt. So thank you to everyone who hung on from the first part of the talk, and welcome to everyone who's just joining for the second part of the talk. Today, I'm sharing a talk about our recent paper titled Muscle-Driven Simulations and Experimental Data of Cycling. In the second part of the talk, we're going to be going through some best practices and tips for using OpenSim Moco. As a reminder from the first part of the talk, we shared our three-dimensional muscle-driven musculoskeletal modeling pipeline of cycling. And that modeling pipeline started with experimental data collection of 16 participants. And for each participant, we created a participant-specific scaled model. And along with motion capture data, we used OpenSim's inverse kinematics to produce kinematics. Next, we used RRA, the residual reduction algorithm, in order to minimize the dynamic inconsistency between the kinematics and the kinetics. From this, we get an adjusted model and adjusted kinematics, and we use that as input to OpenSim Moco, the direct collocation optimization method, from which we produce or estimate muscle forces and joint forces. Today, we're going to be talking through several best practices when using OpenSim Moco. And the first one is validating outputs, which we will start with right now. It is really important to validate all outputs when running simulations, especially outputs when they're used as inputs later in the pipeline. And one way we did that was looking at joint moments. Although joint moments weren't a direct part of the pipeline that I just shared, in my mind, they were absolutely an important part and part of our pipeline in terms of validation and verification of our model. These joint moments can be obtained with the RRA step or with OpenSim Moco, or in our case, at both stages of the pipeline. And it is really helpful when we generate these joint moments. What we want to do is compare them to literature. So there's a lot of literature out there with these joint moments, and it's great to ensure that for all of our participants, we're falling within normative ranges set by existing literature. And if we're not, that can help guide us with some questions about what might be going wrong. We can dive deeper. One way that we can dive deeper is comparing the individual moments produced by the muscles to the joint moments. So, for example, if let's say our ankle dorsiflexion moment is peaking too much right around this peak right here, what we can do is we can see all of the individual moments produced by the muscles that create that joint moment. And then we see, oh, wow, like this muscle is certain muscle is producing a lot of moment, whether that be active force or passive force. And then we can kind of start figuring out why that might be and if it is correct or not. Similarly, we can look at the moments produced by the coordinate actuators to the joint moments. And we haven't talked too much about coordinate actuators yet, but I promise we'll talk about that later in this talk. Next up is ensuring that our muscle paths are realistic for the motion. So the way that we did this was manual adjustments of the iliacus and psoas muscle paths. And this is done in the OpenSim GUI. So what you're looking at right here, in red, we have our muscle path. And in blue, we have that wrap cylinder. And so since we scaled the OpenSim model for each of our 16 participants, we noticed that at times this muscle path was inside this wrap cylinder, which should not happen. That wrap cylinder should be there such that during scaling and motion, we have our muscle path staying outside of that wrap cylinder, since we only have our skeletal model. So in order to get around this, we made manual adjustments for the iliacus and psoas and pulled these via points, which you can see right here, or it was really just this via point, right outside, just a teeny bit to be outside that wrap cylinder to create that smooth muscle path for smooth motion. Next up is simplifying the model when possible. This is kind of always best practice during simulation. And in particular, for these simulations, we made some model adjustments to help with convergence. So that first model adjustment is using minimal degrees of freedom. So we've replaced our locked joints with weld joints. First, locked joints are joints that we felt did not contribute to the motion. Were not really measured. So for example, when we look at this for cycling, we see our subtalar joint with the axis right here and our metatarsal phalangeal joint right here. So during cycling, we're not getting too much of the side-to-side motion, or our toes aren't kind of going in and out. So, or at least not contributing to the part of the motion that we're interested in. So in the first part of our pipeline, so for that inverse kinematics and the RRA, these joints are locked, and that's in the OpenSim GUI. And this can also be done in the API. And so during OpenSim Moco, we replace these locked joints with weld joints. So that's removing a degree of freedom that the solver must meet when solving, when optimizing for our muscle forces. So it helps with convergence, one less degree of freedom for the optimizer to worry about. Also, we use smooth and differentiable muscle models. So for our OpenSim Moco simulations, we use the de Groot Fregli muscles, as these are smooth and differentiable and really help with convergence. Next up is checking for excessive passive forces in the range of motion. So we talked about this a little bit, or alluded to it a little bit when we looked at joint moments. And when we started looking at some of the pretty significant passive forces when we're in deep flexion for these models. On the x-axis, we have the percent revolution of the crank cycle going from 0 to 100%, which was talked a little bit about what that crank cycle is in the first part of the talk. In the y-axis, we have the muscle force in newtons. So now we have a full picture of all the muscle forces. We have our total muscle force, which is here in blue, and then we have our passive force just below it in red, and then our active force. So our active force plus our passive force equals our total force. And this is averaged across all participants. And what we notice is that passive force, that red or pink line, is sitting very, very closely to our total force. So this soleus is putting out a lot of passive force and excessive passive force that shouldn't be there, and can be driving the moment to be large, can be driving co-contraction of antagonist muscles. So in order to circumvent this, we did a soleus optimal fiber length adjustment. So based on the Rajagopal full body gait model, we adjusted the soleus by 1 standard deviation, or the optimal force, optimal fiber length adjustment by 1 standard deviation. And so when we do this, we see our passive force, and I would like to point out that between these two graphs, our y-axes have changed. And we see that our passive force is lower, our total force is lower, and now our total force in blue is a sum of that passive force in red and the active force in yellow. And finally, if we look at the passive forces side by side, in the dashed line, we have the passive force with no soleus adjustment. In the solid line, we have the passive force with soleus adjustment. We see that there is quite a significant drop in passive force, which is exactly what we wanted. And this didn't really affect the passive forces of the other muscles in the model. Next, we really want to ensure that the muscles are driving the motion. After all, this is a muscle-driven musculoskeletal pipeline. And so in order to ensure that, this is when we're going to talk about the residual and reserve actuators, as well as their optimal force properties. So when we do our experimental data collection, we measure the reaction forces at the pedals. However, we don't measure those reaction forces at the saddle or at the seat. And so we need to account for those. And the way that we account for those are residual actuators. So we have 6 residual actuators at the pelvis, one for each translational degree of freedom, or DOF, and one for each rotational degree of freedom, shown right here. And what these are doing is they're capturing that pelvis saddle interaction. And we give them an optimal force. We give them a large optimal force. So this optimal force property was set to 100 newtons for translational degrees of freedom, or 100 meters for rotational degrees of freedom. And what this means is for a control signal, which can go from 0 to 1, and an optimal force of 100 newtons or newton meters, we have that control signal point, let's say 0.5, multiplied by optimal force of 100, we get 50 newtons or newton meters in actuator torque or force. And we want to ensure that this is big enough so that it is fully capturing this saddle pelvis interaction. And it's best practice to check that it actually is. It's the body weight of the rider minus the pedal forces. Using a large optimal force property encourages the solver to use this over other actuation. Next up, we have the reserve actuators. And these reserve actuators are at each additional rotational degree of freedom. So we'd have 3 at each hip, 1 at each knee, and 1 at each ankle. And what these are doing is they're taking care of some of the high frequency moments that occur during the simulation, and they're helping with convergence. But it's really important to, once again, we want to ensure that the muscles are driving the motion. So we want to ensure that the actuator torque is less than about 5% of the total joint moment. So that's the moment I was talking about a few slides ago. And this model was deemed weak in hip rotation based on squat and sit to stand simulations. And so that degree of freedom required a little bit of additional actuation. So we set our optimal force property to 0.1 newton meters for all of these degrees of freedom, except for hip rotation, which was set to 10 newton meters. So this small optimal force property discourages the solver from choosing the optimal, using these reserve actuators over the muscle forces, or the muscles to produce that force, but it's still helping with some of the high frequency moments to get this simulation to converge. Finally, we get to the last best practice, which is tuning the optimization objective function. So here are the objective functions that we looked at in the first part of the talk. And when I look at these functions, I mean, one of the biggest unknowns when I look at them are these weights, and it's how do we pick these weights? So we're going to dive into that a little bit right now. What I've shown here is a screen capture of the solution file after we solve a Moco problem. And for those who have used Moco, you might be familiar with this, and you see all of the good stuff right here, which is our controls from all of our muscles and all of our coordinate actuators. And those are great, because how do we figure out what's driving the motion without those? But I also want to point us to the header. This is really helpful and full of helpful information. In particular, today I want to draw our attention to these few lines right here. So these lines pertain to the objective function. And that first line is we see our absolute value of the objective function. And then we see the value of each of the cost terms that add up to this objective function. So we have that auxiliary derivatives term, the excitations, and then the tibial-femoral force terms. And we look at this section of the header, we can ask ourselves, what is driving the objective function? So we can compare the cost terms values, compare them to each other, and can see how much of the objective function they're taking up. So for example, we can see that for this objective function, our excitation and actuator term is basically entirely taking up the objective function, which is exactly what we want, because we believe that that is physiologic. That's creating a physiologic simulation. And then we have some contribution from each of the tibial-femoral forces from each leg, the left and right, and then just a little bit from that auxiliary derivatives term that we talked about in the first part of the talk. So this makes sense, but this is the final result. So how do we even get there? And so now we can bring back these objective functions. And what we want to ask ourselves when selecting these weights is, at which cost term weights does the solution stabilize? And this is a very iterative process. This is absolutely not one and done. And there are many sensitivity analyses that are performed um, when determining these weights. And so let's talk about the first weight, weight one, or W1 first. And when we were selecting W1, we put a bunch of different weights out there. You can try a weight of 100, a weight of 10, a weight of 1, a weight of 1 times 10 to the negative 10. You can try all of these weights, and as long as you get convergence, then we can compare the results and see when the solution stabilizes. And what does that mean? What I mean by that is, at what muscle activation, or at what weights are the muscle forces not significantly changing from simulation to simulation? So when does our solution seem to stabilize? When are the muscle forces no longer changing? And we wanted to get this weight as low as possible with the solution stabilizing, so those muscle forces not changing. And we selected a W1, or a weight 1 of 2. Next, we have this auxiliary derivatives term. And like I talked about in the first part of the talk, this is an additional, these are additional controls that we need to minimize based on the Moco implicit tendon dynamics. And so we want this to be there, but we don't want it to be taking up a big part of our optimization. We don't want it to be weighted too high. So we landed on 1 times 10 to the negative 6. And finally, weight 3. So this is the weight for our tibiofemoral forces. And I would say this is where the bulk of our sensitivity analyses occurred. So this is a lot of the iterations over and over again, selecting this weight and understanding if it resulted in muscle forces that were create a physiologic simulation. So it's important to pick a weight that penalizes these tibiofemoral forces, but not so much that the muscles that cross the knee are not going to be producing any force, as well as not so little that it's not really penalizing these muscles at all. So after many iterations, we landed on a weight of 1 times 10 to the negative 3. And finally, we're going to bring back these coordinate actuators. And during each stage of the iterations of these objective functions and optimization, we want to be checking how much force that the coordinate actuators provide. So as a reminder, these coordinate actuators, the torque that they're putting out is the control multiplied by their optimal force value. So we really want to make sure that the optimal force value is being tuned each time, or checked and tuned each time we go through these iterations as well, checking that the moment created by these torques, or the torque actuators, or the torque itself isn't too large compared to the moment, but it's also providing enough actuation, for example, with the hip rotation, which this model is deemed a little bit weakened. As a review, we talked through several different OpenSim Moco best practices today. We talked through validating outputs, ensuring the muscle paths are realistic for the motion, simplifying the model when possible, checking for excessive passive forces in the range of motion, ensuring that the muscles are driving the motion, and tuning the optimization objective function. And if you wanted more best practices or more help, I would like to point you to the OpenSim documentation, now at Confluence, as well as the OpenSim forum, where you can ask questions and get answers, and the OpenSim Moco specific forum, where you can ask questions and get answers as well. Those are all very helpful. And I would like to give another giant thanks to my co-authors who helped teach me best practices. Thank you so much, Anthony, Carmichael, Monica, and Scott. And I'd also like to thank Stanford Mechanical Engineering, the Neuromuscular Biomechanics Lab, and the WuSci Human Performance Alliance for funding. And now I'll take some questions.
Great. Thanks, Kate. Now we'll go ahead and switch back to questions. I think we have enough time. We'll probably go back to the ones that came in earlier, and then we'll just kind of work our way through. So there were a few questions about how long this simulation took to converge, I guess. So maybe you can talk about how long each participant was taking. And there was a question about if we've made any progress in automating that method. And I'll just plug and say that we're working on that, and some new features will be coming soon that will result in some speed ups for these simulations. But how long was each participant, I guess is the question.
Yeah, that's a great question. And I would say that that it would differ from iteration to iteration. So, and it also differs from computer to computer based on the computing speed and how that computer is set up. I was running these simulations on a desktop in the lab, and they took somewhere between 30 minutes to an hour, about just about, I believe, in like the last round of simulations. Um, Going through all those iterations. So, but that was not the case earlier. There would be simulations that would take hours and maybe not even converge because of how I set it up. This also depends. We didn't talk about some of the other parameters in the model, such as the convergence tolerance and those kind of parameters. So to help it converge, you can make those parameters larger to start and then kind of narrow and small and make that a little bit smaller for your convergence criteria. And then if you add more cost terms, I would imagine that the optimizer has to work harder, and then we're going to have even longer simulations. I know Matt uses Moco, so he might be doing some like really big simulations, and if you're doing multiple cycles, that will take even longer. That's kind of a really open question, and then predictive simulation will be even longer
Yeah.
days. So it really depends on the simulation.
Yep. Definitely. Um, I guess a quick question about including the minimizing tibial femoral force. Amir Saimi was wondering if you considered minimized tension instead of minimized force while you were trying different objective functions.
Yeah, that's a good question. So that's actually what the force is called in OpenSim Moco or in the model. It's that tibiofemoral compressive force.
Okay.
Um, and we minimize both in the two knees.
Um, and along those lines, Jalen Hamad was wondering which Moco pipeline you were using, one, but two, how did you incorporate the tibial femoral forces? Was it creating a custom goal, or were those there states in the model that you could include easily into the objective function?
Yeah, that's a good question. I used Moco inverse, but I also in the code invoked several features from the overarching Moco problem. If the words I'm saying make zero sense, that's completely normal. And I would direct you to the Moco paper, in which they understand the hierarchy of Moco inverse, Moco problem, really well. But I did use Moco inverse to solve this. And the second part of the question was about the cost term. So for each of the cost terms listed, when we looked at that header file, for example, well, we add a cost term. So that would be in the code, adding a cost term, selecting what we want to minimize in that cost term, giving it a weight, and adding it to the problem.
David Hostman was wondering if you manually were performing the steps of IK, RRA, and Moco, or was it like an automated MATLAB script that you were using?
That's a great question. I was actually manually using it. When I was developing that part of the pipeline, it was before I had learned the API. So I was doing that all manually in the GUI. However, yeah, if you are comfortable with the API, you can definitely do those there as well.
Amir Saimi, another question about how you made those adjustments to the muscles to compensate for the passive force. I guess you changed the optimal force, but was it an iterative process, or maybe you could speak a little bit more about how you played with that?
Yeah, so that was just for the soleus. That was the only muscle that we were updating the optimal force, optimal fiber length property. And it was kind of later in the process when this passive force from the soleus just like would not go away, no matter what we were throwing at it. And so we were based on the original models, or like the models from which our models were originally created. So that would be the Lie-Arnold model, and then that was a high flexion model based on the Rajagopal model. We saw how all the parameters were developed. So that's how we determined to increase that optimal fiber length for this layers only for all participants by 1 standard deviation. And that scaling was done in OpenSim Moco. So if you download the code, you can see exactly where that's done.
Combined questions, I guess, from Muhammad Muhez Ahmed. I'm sorry. In terms of the coordinate actuators, he's asking, do they add force in addition to the muscles? Like, do they work in conjunction? And then second question to that is, should those actuators be adjusted for each person, each of the 16 participants, or did you find a value that worked for most everyone?
Yeah, these are some great questions because those coordinate actuators are really tricky. So for the first part of the question, the torque or force put out by those actuators sums with the force and then the torque for the muscles to create that joint moment. So it's all additive. I mean, some of them will go negative, some will add, and then we'll add them all together, and that will create that joint moment. And then for the second part of the question, which is we made it generalizable. So that's why this was so iterative. So we made sure that these coordinate actuators, their optimal force properties were working across all participants. But the way that we did this, we didn't start with 16 participants. We started with 1 and then went to 4 and then went to 8 and made sure that at each stage that the process, the pipeline that we were making scaled. So it was definitely like 1 participant do a lot of, it was like participant number whatever doing participant 12 a bunch of, who became participant 12 a bunch of times, and then going to 4 participants and building that up and up and up. But it's good practice when developing a robust pipeline to have the parameters the same for all participants.
And a similar question is actually the next one in terms of the cost function. It's from Jawei Gao. In terms of it's the same idea, right? In terms of the cost function weights, it's a similar iterative process of like kind of find one that works and then see if it works for everyone, right?
Yeah, absolutely. So you're not only iterating like all these, you're iterating quite a few things. Like that solution space is quite large. You have all your weights, you have your all of your coordinate actuator optimal forces, and then you also have all of the participants. Yeah.
Definitely. Jalen Hamad, a question about how did you select the constraints for your convergence tolerance for your objective function, and did you have to change the default values to account for the for your total objective value?
Yeah, that's a good question. I definitely did change the defaults unless I went back to the default, but I have it hard coded in whatever I used. I think that when producing the simulations, at first I was using a larger convergence tolerance because I was trying to help the solution solve. But if the convergence tolerance is too large, it's actually kind of not helping the simulation, because you're going to get kind of some junk because it's going to not get close enough to the solution that it's a close enough solution. I think that there are some really great Moco tutorials when you download Moco or OpenSim Moco. And those give some examples as well as some of the OpenSim documentation to kind of hit that sweet spot.
Definitely. Miko Horston was the question about muscle wrapping. When you're having issues with the muscle wrapping, would you recommend changing the via points of the muscle path, or scaling or moving the wrapping object with the model scaling, and any specific cases where that might be better or worse, or did you consider each of those options?
Yeah, that's a good question. I didn't consider moving the wrap cylinder. I think that wrap cylinder is like a geometric constraint. So like when we have our skeleton, we're not like we don't get that like our full thigh modeled in, for example. So that's what that wrap cylinder is doing. So I manually adjusted those via points to do so. As a teaser, I believe that there's a new, OpenSim developers have told me there's going to be a new algorithm coming in that should also help with this. But that should be checked anyway. And when I did those via point adjustments, I did it manually in the GUI, and I was typing like the smallest change as possible just to see that to the via point to get that muscle path pop outside of the wrap cylinder.
Yes. A question from Brecca Gaffney. Well, we talked about what Moco problem you used. It was a Moco inverse. I guess the second part of the question, just to bring up, did you implement an initial guess at all in your solution? Or,
no, this problem didn't have an initial guess.
Yeah. I guess there's a question. There's a question about left and right sides having different weights. That may have been that there was different objective values, I think, in the objective function. I guess, is that something you saw where there was a different objective value for each side?
Yeah, that was a good question. So the results that we presented were for the right leg only, just for clarity. You could have chosen the left leg. The time matching is a little hard because it's opposite with the two legs. So the graphs were way less pretty with both. But the reason for that is you're not going to be putting out the exact same knee moment on both sides in the same cycle. Like it's just sometimes there is in the cycling community, there's all different types of strategies. Sometimes people will like push really hard with their right leg or their leading leg. A lot of us are righties and lefties, and if we play sports, we may have a stronger leg. There could be any number of reasons, and so those values were very close, but not exactly the same. And those are some of the reasons why that could be.
Maybe it's kind of talking about the tuning, I guess, again, in terms of did you test the cost function? I mean, you had the different cadences and different speeds. Did you like find that like when you were optimizing the cost function maybe for a slower speed that it didn't work for the higher speeds, or did it generally work across all of them? Or maybe you could talk a little bit about that process.
Yeah, it did generally work across all of them as I was adding in participants to get that full spectrum. I would say that the original data that was collected was for more than 16 participants, and so we used a subset of that because this pipeline was a bit longer. And we tried to select participants that had the best normative range kinematics and then moments as well. And the reason for this is there's one participant in particular that I remember we were like, do we put it in? Do we not? And this participant was putting out a ton of power. And they were from Anthony, who collected this data. He said like incredibly fit person, but maybe not a very experienced cyclist. And so there may have been some compensatory movements to produce all those moments required to output a power like that. And so for this study, we took that out so that like kind of to get at what the question was originally asking, like that this pipeline did work for all of the powers and all of the cadences with like those normative kinematics and moments.
Well, unfortunately, we are out of time. So thanks again, Kate, for a great talk and best practice session. And thank you for all the great questions that have rolled in. Please be sure to click the link that will appear at the conclusion of the webinar and take our survey. That'll help us improve the webinar series and choose upcoming topics. This webinar series is supported by 2 grants from the NIH, including the grants that support our Mobilize Center and the Restore Center. We're grateful for the support, which allows us to run these webinars and other events. Thank you again to everyone for participating. We'll hope you continue to stay involved with our centers, and that we'll see you in a future webinar. Have a great day.